Today we are going to do section 5.2. What is this? Power functions and polynomial functions. A power function is actually a kind of polynomial function. It's basically what it is something that is to the power of, that's x to the power of something. Okay, and such as let's see, such as x to the power. Let's make up something, 5, okay? Or x to the power minus 1, or x to the power 0, or any of those things. Let me get a better marker. So such as x to the power 0, okay? This is a 0 here. Or some other number, x to the power 10,000, let's say. Well, I'm tired of writing 0, or negative 10,000. So anytime you have x to some power, that's called a power function. X to the power 0, of course, equals to 1. Okay, this is 1, and the others are just whatever they are. You can also, it might have a number in front, say, let's say 5 minus 2 or something. Some other number, say 0.5 or 1/2. 1/3, let's say. Anyway, all these, it can have a number attached to it, and these are all called power functions. So let's turn to the page, the next page, to look at example 1. Okay, we have entire list of various stuff, and if the power can be a fraction. Okay, for example, x to the power 0.5 is fine. That's a power function as well. And as you might remember, that's also written as a radical. This thing is called a radical, and it means to take the square root of x, and these two are the same values. The square root is the same as to the power 1/2, or you can also write it as x to the power 1/2, like this. Okay, 1/2 the same as 0.5, the same as square root of x. And similarly, if you have the cubic root of x, that means x to the power 1/3. Okay, to the 1/3, or put it another way, is you need 3 numbers when they multiply them by themselves. 3 identical numbers that when they multiply by themselves will become the x. That is, the cubic, as an example, would be the cubic root of 8 would be equal to 2. Because 3 of the 2's, you find 3 2's, they multiply them together, then it will become 8. Anyway, so that's just a reminder of what the cubic root is. So for example 1, every single thing in there is a power function. Next, let's consider the end behavior of power functions. The end behavior means what happens towards the end. And what's the end? End is when x goes to infinity or negative infinity. Okay. For example, let's flip a few pages. What page am I on here? Page 422, where we consider the end behavior of x to the power 8. Now, what that means is what happens, you just imagine when x goes to infinity, what happens to it? When we think about infinity is too big, so let's consider, I don't know, 10, okay? What happens when x is 10? When x is 10, x to the power 8 is 10 to 8 zeros, okay? And let's draw, how many zero do I have? Well, whatever this number, right, that's if x equal to 10. So x equal to 10, then x to the power 8 will be equal to this thing. And then, x to the power 8 will be equal to this number that I just wrote. Now so what that means is as x goes to infinity, then x to the power 8, that is, as x get bigger and bigger, x to the power 8 will also get to go to infinity. Okay, and it's going to infinity very quickly because it's a power 8. So you got 8 zeros each time. For each 0, you get 8 of them, and then if you have 2 zeros, you have even more. So a ton more. So that is the conclusion. And on the other hand, you ask yourself, what happens when x goes to negative infinity, or let's be simpler. Let's say x goes to minus 10. Then x will multiply itself by 8 times. That, in other words, there's 8 of them multiplying by themselves. Then the negative sign shows up 8 times, like this. Okay, let me write it out. Minus 10 times minus 10. And okay, I'm tired. Let's imagine I wrote down minus 10 8 times here. Okay, so and you have all this, but the negative sign then show up 8 times, which means it's still positive. So as x go to negative infinity, then the value still go to positive infinity. That's negative infinity. The reason is because the power is an even power. Anytime you have even powers, then the negative sign appears even number of times, which means they cancel out each other. As a result, then the function then still go to positive infinity. Okay, and so that is for example 2. Now what if I have not an even power but an odd power? Let's say x to the power, say 7. Okay, what happens when it is x to the power 7? Then if the function is x to the power 7, then the story will be different, because if x goes to positive infinity, like x is 10 or something, then x to the power 7 is going to be very positive, a big positive number. Okay, so x goes to positive infinity, then x to the 7 is also going to positive infinity. But the question is, what happens when x becomes very negative, goes to negative infinity? Let's say x is minus 10. Then when you have minus 10, 7 of them, okay, imagine 7 of them multiplying together, you have one negative, and the 6 of the negative signs will cancel out, but there will be 1 left. And as a result, as x goes to negative infinity, x to the power 7 will also go to negative infinity. That is, that's for the odd powers. And in general, when the power is even, then it goes to positive infinity either way. Okay, and whereas if the power is odd, then it goes to positive infinity if x is positive, and goes to negative infinity when x is negative. Now to graph this thing, it will look something like this. Okay, x to the power 8, when x is positive, the function goes positive. But when x is negative, going to negative infinity, the function is also positive. So it looks kind of like a bow. And whereas the odd, that this is x to the power 8, or any x to the power 8. Why do I keep writing the equal sign? Okay, let's get rid of that. So x to the power 8, or any even power, excuse me, any even power would be rising on both ends. Very much similar, very much similar to x squared function. It looks similar. And then whereas x to the power 7, it will similarly go up. Okay, when x is positive, the function will go up. But on this side, it'll go down. Okay, when x is becoming negative, the function will also become negative. And that is this is some odd power functions, such as x to the power 7. Okay, so that is example 2. Okay, and then let's look at example. Next, let's look at the example 3, where you have an x to the power 9 situation. The only difference here is there's also a negative sign slapped in front. That just means if you have the function got flipped around, and you can see that. Let's see, what page am I on? 423. So you can see that if let's say we have x to the power minus, and our function is negative x. Okay, so negative x to the power minus 9. Now in that case, we have x, you just check some number, okay, that's fairly big, such as, let's say in this case we checked x equal to 10. If x equal to 10, 10 to the power minus 9, negative 10 to the power minus 9. No, sorry, it's not minus 9, it's 9. We're not dealing with that. All right, 9. All right, that's better. So we have minus x to the power 9. That is a very negative number, okay? So then the function then goes to negative infinity. So as x goes to positive infinity, the function f of x, in this case is minus x to the power 9, is going to very negative, a giant negative number, negative infinity. And then when x goes to negative infinity, because it's an odd power, this function without the minus sign will go to negative infinity as well. However, with a minus sign, it changes the negative to positive. So f of x, which is minus x to the power 9, will go to, let's say, positive infinity. Okay. In other words, the normal sign got flipped over. And so this thing will go to negative infinity, and then as x approaches the positive infinity, and then go to positive infinity where x is going to negative infinity. So that is does the opposite of what that one does due to the negative sign in front. In general, if you just test some number in there, just some convenient number such as 10 or minus 10, then you can quickly figure out which way this thing is going. And that's called the end behavior. The end means when x goes to positive or negative infinity. Although in reality, we only think as much as 10. But you can imagine a giant number if you want, like a billion or 10 billion. Okay, what if x is 10 billion? Where would f of x go? Or if x is minus 10 billion, what would f of x be? That sort of thing. Anyway, so that's that. Next, let's look at polynomial function. Let me erase the board. Next, let's go to page 224, example 4, to identify the polynomial. The polynomial is often written like this in the general form. That is, the polynomial is a number called an times x to the power n. N can be any number, okay? The number n is called the leading coefficient. That's the most important coefficient. That is the highest power of the polynomial. And the an is whatever number that's in front of it. And similarly, an minus 1 is the next next term in the polynomial where x is now 1 power less. That's why it's called n minus 1. And then an minus 1 is whatever number that's before it. We call it an minus 1 to show that it is the number in front of x to the power n minus 1. And then an is the number in front of x to the power n. So the x power goes down one step at a time, okay, until we finally got down to a2 to the power x2, and then a1 to the power x, and then a0, it has no x, okay, because it ran and there is no more. Remember the a2 with a subscript 2 or an with a subscript n, it represents one variable, okay? It's like the variable has a number to it. It's like somebody naming their kids. Isn't there some rhyme that says some woman has 23 kids and they're all named Dave or something like that, right? And that this is the same thing. You have all these numbers are named A, so to tell the difference, we will call them A1 and A2 and A0 and so on. And the numbers will correspond to the power. That way it helps us remember it better. Okay, a nice system. Now this looks like an extremely complicated formula with lots of symbols, numbers, whatever. But in reality, it need not be complicated. For example, an example of polynomial is right here. F of x equal to 0 is a polynomial. Why? Because that just means that all the an's are 0 except for a0. Actually, a0 is 0 as well. Okay, everything's 0. And it's still a polynomial because the definition doesn't say that an cannot be 0. In fact, a lot of times they are 0. Okay, but the an cannot be 0 because then we wouldn't be writing it. All right, so an is assumed to be not 0. Everything else can totally be 0 if they want to. Here's another example, okay? Here's x cubed minus 1. This polynomial, as you can see, is mixed. Where's x squared? or x. There's no x squared. You see, x, that is a2 in this polynomial equals to 0, and so is a1. Okay, there's nothing in no x here either, and that's perfectly okay. The a's can be any value including 0. Any real number including 0. That's perfectly acceptable. The only thing is, yeah, an cannot be 0, because then we don't care about it, because there's in front of the 2x, you can say there's a 0 times x to the power squared, but yeah, it's 0. We're not interested anymore. Okay, so the highest power is called the leading coefficient, and that is the first the non-zero number. That's the highest power, and we give that a name, and that's the degree of the polynomial. So anyway, so this thing has a degree of 1, that thing has a degree of 2, that thing has a degree of 3, and this thing has a degree of 100. All right, and then the polynomial. So while this equation might look complicated, it doesn't have to mean anything complicated. It can just mean that or that. Okay, that's a quadratic function, which is a polynomial as well. Yeah, and then I wrote another example to drive the point across. Is that excuse me, is that n, the power n, can be anything. Okay, so I wrote one with 100 in it. And what's the dot for? The dot is for when you're too tired to write anymore. As a result, imagine this function right here, which I have just made up. Okay, and what it is the function will be I don't know why there's a minus sign there. Let's keep it simple. We'll keep it positive. And so the function I made up is 100 times x to the power 100 plus 99 times x to the power 99 plus 98 times x to the power 98. And then I ran out of steam and I don't want to write anymore, which is why they did this. Okay, but you can imagine. And then there's 97 and 96 to the power x to the power 96 and 95 and and one at a time until you always finally got down to the last few terms. You got down to 3 times x to the power 3 and 2 times x to the power 2 and then just 1 times x to the power 1. Okay, we don't write down 1, but there's a 1 here. And then finally, 0. Yeah, finally it's a 0. Should to follow the pattern, it should write down 0, right? Yeah, so let's no, x to the power 0, yeah, it's 0 because it becomes 0. My pattern says 0, yeah, so that's 0, right? This is just 0. But anyway, to follow my pattern. But so you see why we write things this way, okay, with the dots and all the numbers to represent anything you can think of. Okay, here's a polynomial I can think of. You can come up with one that says 1,000 for anybody cares, right? And then your polynomial will have 1,000 terms. And it goes on, and it will take you a while to write it out. So it's better to write the ... here, so you don't have to write all of it. And that, of course, is only if your polynomial follow a very fixed pattern like mine. If your polynomial have just random numbers, 3 here, 5 million there, then you have to write it all out if you need people to know what you're talking about. But we don't. No, we don't deal with polynomials that big that I know of anyway. So that is. That is that. What we were talking about, example 4. So let's look at example 4. I lost the page. What is that? Yeah. Okay, example 4. Let's look at the following page, where it says we're identifying these functions to see if they're polynomial or not. Now, polynomial is some number times x to some power, and that power has to be integer, by the way. Okay, I don't have any fraction here because the power has to be an integer for polynomials. As a result, let's look at example 4. We have 3 functions. That's a polynomial. That's after you multiply it out. Same thing here. That will be a polynomial after you multiply it out. H of x is not a polynomial because it has a square root function, and the power has to be integers, regular numbers, not a fraction, which is what a square root is. So with that, I already told you what this number is called the degree of the polynomial. Okay, and these numbers are called coefficients. And then yeah, and this thing, the highest degree number is called the leading term, which yeah, well, you will know that eventually because it will refer to it like that off and on. It is like learning the name of some kid in your class. Eventually you get it. You don't have to study to do that because you hear it enough times, so then eventually you got it. So let's flip the page. What am I doing here? Did I do example 5? Where's I'm missing? Okay, here is example 5. Okay, so let's go to example 5, where you are supposed to identify the degree. Please do that yourself. Okay, I don't think that requires much teaching, and what leading coefficients are and all that. And then let's turn the page to next one, example 6, the end behavior. Again, please do that example yourself. The end behavior, as I mentioned earlier, is you have to calculate you have to estimate what happens when x goes to positive or negative infinity, which in practice just means you let x equal to 10, okay, and see if it gets really big or really small. The thing is, however, you might ask the question, but there's all these things, so which one do I test? You only have to test the one with the highest power. That's the leading coefficient. The reason is because the one that has the highest power determines what the end behavior. Okay, all the rest of the stuff that's less don't matter at all. Just so to calculate the leading power, you will check, say, the 2x in this function, or x squared in this function, or together with this coefficient, because the coefficient might make it positive or negative, right? Because it's slapping a negative sign here, will make as x goes to infinity here, right? X is, say, 10, then the x cubed will be 1,000, but the negative sign made it negative 1,000. So then x goes to infinity here, this value, it will go to negative infinity. So you have to watch out for that thing. And then, of course, this thing, as x goes to positive infinity, that is so going to positive infinity. The rest of it don't matter. Okay, and so that's how you calculate end results, which is end behavior. That's example 7. Please do that as by yourself. All right, local behavior. And the next thing we are going to talk about is a polynomial will have, of course, x-intercepts sometimes. Yeah, sometimes they don't even have x-intercepts, but when they do, what is an x-intercept? An x-intercept, it was when the polynomial crosses the x-axis. Okay, here is, let me see, what page am I on? I'm now on page 429. Let's see. Okay, anyway, I'll write it right here. So right now we're on page 429, and I'm looking at some graph on it, which I will show you. For example, this is a polynomial, and it has x-intercepts, which is the point where it crosses the x-axis, where the values there. The x-intercepts are also the zeros of the polynomial, because that's when the graph becomes 0. However, the zeros, however, might not cross the x-axis if the zeros are complex. But we're not going to talk about those things right now. Okay, we're focusing on real numbers. So if the zeros, are also called roots, are real, then it crosses the x-axis at some point. And so anyway, so those are called x-intercepts. Now the turning point is just when it turns. Okay, it turns at a place that's called a local maximum, and that's a local minimum. That's also a turning point. Then, well, sometimes it isn't. It depends on how it turns. But in this case, it's a local maximum and local minimum. But anyways, the turning point just means it stopped going up and start going down, or stop going down and start going up, and that's why it's called a turning point. Well, I don't think that. Well, anyway, let's not think too much about it. The next, let's determine the x-intercepts, the y-intercept and the x-intercept. That is example 8. So let me erase the board. Next, let's look at example 8 on page 430, where we have a polynomial already factored. But it's still a polynomial, factored or not, okay? You can imagine that when you multiply this thing out, it will look like some polynomial. The point is we are looking for the x and y intercepts or something. Yeah, so the x-intercepts are exactly where the polynomial equal to 0, which means each one of these things has to be equal to 0. In other words, x minus 2 has to be equal to 0. Okay, because that's the only way it'll cross the x-axis is when these things, at least one of these things are 0. So x minus 2 can be 0, which means x crosses at positive 2. So x equal to 2, or I'm writing it too close here. Anyway, so next x plus 1 has to be 0, which means x equal to minus 1. And lastly, x minus 4 has to be equal to 0, and then x will be equal to positive 4. When you move the negative number across the equal sign, it becomes positive. So this particular polynomial crosses at x equal to 2, x equal to minus 1, and x equal to 4, the x-axis. So these are the x-intercepts. Let's see. And then the y-intercepts, on the other hand, is just what happens when x equals to 0. Okay, so the exact x-intercept are supposed to be written like this. You write down in coordinate form. Okay, see right here where we have the x-intercepts are called minus 1, 0, 2, 0, and 4, 0. Those are the points on the x-axis, their exact location. But I just wrote down the x's here. That's good enough for me. And so the y-intercept similarly is when does this thing cross the y-axis? That's usually much easier to do because you just imagine x equal to 0. And when x is 0, then this becomes f of 0. Okay, I draw a 0 there. That's a 0. Yeah. Anyway, so that is a 0. So that becomes minus 2 times positive 1 times minus 4. That should be positive 8. And so the y-intercept will be called x is 0 and y value equals to 8. That should be the y-intercept. Yep, and that's what the book did at first, because the y-intercept is easier to calculate. And for any function, there's only one y-intercept, but there will be a bunch of there might be a bunch of x-intercepts, or there might not be any x-intercept at all. Okay, for example, let's consider the function say x squared. Here's x squared plus 1, okay? And x squared plus 1 doesn't ever become 0 because you're squaring a number, so then and then you're adding 1 to it, then this whole function is at least 1, okay? The lowest point will be 1, and then after that, whether it's x is positive or negative, it will become more than 1 because you're squaring it. So this function has no x-intercepts, which is okay, okay? It's still a function, it just doesn't have any x-intercepts. But you always have a y-intercept because you can always set x equal to 0 and you come up with some value for the function, which in this case, a y-intercept would be 1. But anyway, that should be example 8. And then next, let's look at example 9, okay, something that is done frequently. That is, we need to determine the polynomial function that isn't beautifully factored for you. Okay, this thing is handed to you on a silver platter, but you're never going to see that in your homework. What you're going to see is something like this. f of x equal to some function, and you have to figure out what you have to factor yourself. Okay, so that in this case we have x to the power 4th, and then minus 4x squared and minus 45. All right, so then this is a 4th power, but luckily although this isn't factored for us, it still handed us to on a silver platter. At least a shiny one, because this is actually a quadratic, looks like a quadratic function if you pretend that x squared is a thing, because this is just like, let's call x squared equals to y. or z. Maybe z is better. I don't know. And is z better? Or maybe w. W is better. Okay, I like w. Okay, let's call x squared equal to w. Then this whole function get turned into x w to the power squared, because x squared is w, so x fourth is w squared minus 4 w, okay, being that w is x squared, and then minus 45. And then if we see it that way, then this is likely this is much easier to solve because this is a quadratic function. So we can, in the worst case scenario, apply the quadratic formula and factor this thing, no matter what. But in this case, I think we'll have it easy, okay? Because it's 45, and you have to crank out 45 and then somehow come up with 4. Then we will do 5 times 9, all right? So 5 times 9 is 45. And then we need this to be negative, so we'll have a negative 9 and positive 5. That will give negative 45. 5 times 9 is negative 45. And then minus 9 plus 5 will give the minus 4 to create this effect. And what we're doing is we have to come out with this thing, okay, that when you multiply them together, it better be that. So that is messing around and trying to get it to work. It doesn't always, there's not always possible to do this, but in easy cases such as this one, it is possible, which means we got away with it. Okay, and so then from here we get that w is equal to 5 minus 5, I mean, okay, because w plus 5 is 0. So w equals minus 5, or w equals to positive 9. Now, which means, well, being that we only accept real numbers at this point, we will ignore the complex root, I believe. Well, yeah, so let's ignore so x squared cannot be negative, so we'll ignore this solution and only get w equals to 9, which gives x has to be equal to plus or minus 3. Okay, and so that should be the two, what are we doing here? Right, the intercepts. We're looking for x-intercepts. So complex roots do not provide x-intercepts, so we only pay attention to real root. So the x-intercept will be 3 and minus 3 with y value equal to 0. So anyway, x at plus and minus 3 is where the graph crosses the x-axis. So let's see. Okay, and in the meantime, the y-intercept, which is much easier, is when you set x equal to 0. Well, the y-intercept means x is 0. Okay, what happens when x is 0? 0, 0, minus 45, then y-intercept will be minus 45. And that is that. All right, then so the x-intercepts are 3, 0, and then minus 3, 0. Okay, so we have so then we have all the information that we're looking for. Okay, the x and the y intercepts. Then your book graphed this thing. So it ended up looking like this, as we might imagine. It crosses the y-intercept down at minus 45, and then at plus and minus 3, see, it crosses the x-axis. Now this graph might look a bit odd to you. That's because the graph got really crushed. And you notice that it's going up by 20 units per square, where it's going across by only 3. I mean by only 1. So in reality, the real graph, if it wasn't so crushed, it would look this super long and skinny thing that you can hardly tell what it is or something. So we changed the units so that we can see it better. Okay, but of course this isn't a real look. This is a crushed look, because the whole thing got crushed down by, I don't know, 100 times or 50 times or something like that. To be able to see this graph properly, we have to see it in a distorted or crushed form. All right. So if you as of right now, I'm not going to ask you to plot stuff in the calculator yet, but if you want to, you can plot this thing in the Desmos calculator, and so that you can look at it yourself, what the graph looks like, and also learn how to, well, crush it, okay, so that it looks just like this. Now to type in this function, generally, so we have to type in this thing into the decimals calculator, the only part I want what you're gonna type is yeah, just type that thing in, right? But to do the power 4 and the power 2, what you're gonna do is push the up button, which is the one right here, the one over the number 6. That is, push this thing right here, okay, the number 6, okay. I think you also need to push shift. Yeah, push shift. Then you get that upward thing, and that will move your computer cursor up, and then you'll be able to type all the powers, like to the power 4, and in this case you have to type in the 4. So you push up and you get up there, and once you get up there and you finish typing 4, how do you get back down? Then I believe you can push the down arrow and decimals, okay, which is over here on this thing, or this one. I don't know if this one works. I think you probably have to push the down arrow, or you can move the computer cursor away from it, okay, and then click it, and that would also move the cursor out of here after you type 4. But anyway, yeah, you figure out how to type the 4. That's just push by shift 6, and then how to get out of there, and then keep going until you type the whole thing in, and then that'll give you the graph. But right now I'm not gonna ask you to do it yet, because there are plenty of opportunities to do that. So next, let's the turning points. All right, what are we doing? Let's look at example 10. Determine the number of intercepts and turning points. Yeah, well, all right. Well, we're not really determining it. We're only like guessing. Okay. Generally speaking, let's look at example 10. There's a polynomial, and it has the highest power is at 10. The highest power of the polynomial is normally written first, and that's normal. But if it isn't written first, then you need to change the polynomials to move it to the front. Okay. And so, but that doesn't. Well, most of the time people know enough to write the highest power first for the polynomial. Now the polynomial has this one has a degree of 10. That's the power of the highest term, and so then and the number of roots or x intercepts is determined by the power. That is, if the polynomial has power 10, then it has 10 roots. Okay, and if or 10 roots, and if it has power 5, it has 5 roots, and so on. However, and you do remember that just because it has roots does not mean that the root will cross the x-axis, and because the root might be imaginary, as in this case, okay, then it doesn't cross the x-axis, so then it's not an x-intercept. So sometimes it might have I can write this thing as, instead of squared, I could write it as the 10th power. Let's see, yeah, then okay, and let's write this thing as the 10th power. Now, if it has 10th power, it has 10 roots, but none of them is real. Okay, they're all imaginary, and therefore this one, it does not cross the x-intercept once, despite having 10 roots. Now so that is that, and then it has the number of turning points. Is how does the graph turn? It will turn at the most 10 minus 1 times. That is, if it's 10 power, it will turn at most 9 times. Okay, and most doesn't mean it's gonna get there. And like in this case, it only turned once, right? But other more. If it does have 10 roots, then it will definitely have well, not definitely actually, but anyway, if it has 10 roots, then it has more likelihood it might have, or should I say, it might have 9 turning points. So it turns 9 times somehow. Anyway, that's good enough. Next, let's look at example 11. Okay, what about it? Here's a function. Okay, now you notice that both ends are going up. That means it's an even function, because if it's an odd function, then when x goes to minus infinity, the number of the odd, when you multiply the negative sign multiplying by itself odd in odd number of times, it will end up being negative, and then you will go to negative infinity. The function will. So, so this has to be an even function, okay? And then the even function has, let's see, it crosses the x-axis at some point. What do you call that? -2 point, I don't know, 76, something like that. And then over here, positive 2 point, maybe 4. And so it has 2 x-intercepts. However, it does more turns. Okay, how many turns does it have? It turn 1, 2, 3, right? It has 3 turns. So this is even though it has only 2 x-intercepts, this is actually a polynomial of degree 4 or higher, but at least degree 4, because that's the only way you can have so many turning points. Yeah, if it has degree 2, it'd be a quadratic function. It'd be a nice smooth bow instead of that bump on the bottom. And so this has to be some kind of a degree at least 4. Okay, yeah, which is what the book said, and that is good enough. That's example 11. Next, let's look at example 12. What about this? This is determining, what are we doing? Number 12, we have another function, okay? Now this time there's a negative sign at the very beginning of a function, which means whatever it normally is, we got to remember the negative sign. And then the x-intercept, well, whatever. So please do this example yourself, okay? It's pretty standard. And so by now we have come to the end of the section. Yeah, I'm not going to assign any homework in this section. I don't believe it's necessary. This section is more about concepts like yeah, the number of turning points or the name of the degree, which most of which is you will learn very soon in time. So please move on to the next section. Okay, but first do look over the examples and do the ones that I skipped over, but it's assigned all the way from example 1 to example 12.